This is video 6 of our circuit analysis course. In this video, we're going to cover mesh analysis, and this is part 1, video 1 of 2, part 1. And this is mesh analysis without current sources. So we're only going to look at circuits without current sources today. Alright, but before we get into it, and I have this circuit over here that we're going to analyze, again I want to refresh our memories on our methods of analysis that we have so far. Our tools in our toolbox, so to speak. And the ordering is important. These are the ways that I kind of consider going about analyzing a circuit. I consider first, can I just use Ohm's law? This is very simple. But of course, you can't really, it's typically the case where you can't immediately apply Ohm's law in the circuit. So for example, this circuit, you don't know the voltage across any resistor. And again, I want to point out a pitfall of students I see here. This 5 ohm resistor is connected to this 15 volt source, but you don't know the voltage here. 15 volts is between here and here, not between here and here. So you don't know the voltage across this resistor, so you don't know the current immediately. In fact, in this circuit, you don't know the voltages across any resistors, and you don't know the current through them, so you can't immediately apply Ohm's law. The second thing we looked at was Kirchhoff's laws. Okay, he had 2 of them. To immediately apply his voltage law, you can only have 1 loop. So this has 3 loops. To immediately apply his current law, you can have you have 2 nodes. Well, this has many more than that. 1, 2, 3, 4, 5 nodes. The next thing we looked at was resistor combinations. And with that was, of course, this was series and parallel and delta Y, but with that went voltage division, and current division. Okay, now here we do have resistors in series, so I could combine the 6 ohm and the 4 ohm, and that would make 10, but at that point there's nothing I can do, because I have no combinations of resistors. I can't use voltage division, I can't use current division, because no resistors are in series or parallel, respectively, after the 6 and the 4 are combined. And the last 2 videos we looked at nodal analysis. Nodal analysis. So nodal analysis applies to every circuit. So yes, we can use nodal analysis here, but I want to talk about a different method of analysis called mesh analysis. If you remember, nodal analysis uses number of equations was number of nodes minus 1 minus the number of voltage sources. So let's identify the nodes here. Here's 1. And I'm not going to circle them anymore, but here's 1 node here. Here's 2. Here's 3. Here's 4. Here's 5. So we have 5 nodes. We have 2 voltage sources. So 5 minus 2 minus 1 is 2. So if we use nodal analysis, we would require two equations. So that's certainly an option. Okay, but sometimes if we have a lot of nodes and not a lot of voltage sources, this is going to get messy fast. And so a different method of analysis, okay, the dual actually of this is mesh analysis. So this is kind of 4A and 4B, mesh analysis, and that's the topic of this lesson. All right, well, first of all, let's define what a mesh is. And it's simple. So we did talk about loops before. Meshes are related to loops. This circuit has 3 loops. There are the 2 kind of small ones, right? That is to say, go from node 2 to 3 to 4 to 1, back to 2. That's a loop. Then there's this loop here on the right, 3 to 5 to 1 to 4, back to 3. But there's also the big loop. 2 to 3 to 5 to 1, back to 2. So 3 loops here, but a mesh is a loop that contains no other loops. So that third loop that we looked at, that's not a mesh. The outside big one is not a mesh. But the 2 small ones, those are meshes. All right, so what I'm going to do is define a direction around the mesh. And I usually go counterclockwise. It's just a way that I do it, and I seldom change. If you stay consistent, then you will reduce your probability of error. Okay, so I've chosen directions around these 2 meshes, and I'm going to call this is going to be mesh 1 here on the left, and it's going to be mesh 2 on the right. And I'm going to label these meshes, and I'm going to suppose that a current. Now this is hypothetical. We know that this isn't actually true. Suppose a current goes like this through the 5 ohm. And then all of that current goes through the 10 ohm, and all of that current goes through the 10 volts, and all of that current goes this way. So suppose there's this hypothetical current that's just going around the mesh. We're going to call that hypothetical current mesh current 1, I1. And similarly around mesh 2 here, suppose that there is this hypothetical current that's just going through the 6 ohm, through the 4 ohm, up the 10 volts, up the 10 ohm, and back here. Okay, we know that it really splits off into the branches, but let's just suppose there's that hypothetical current, I2. Okay, those are our mesh currents. So I'll just list those here. Mesh currents, I1 and I2. And again, I chose the directions to be, I think maybe I said, did I say counterclockwise before? Clockwise. So I've chosen them to be clockwise. That's typically the way that I choose, clockwise. But you don't have to pick clockwise. You can pick counterclockwise if you like. Remember, the directions in circuits don't matter. You end up getting the same result in the end if you do everything correctly. All right. Well, I guess we'll list the steps for mesh analysis. Mesh analysis, just like we did nodal analysis. And then when we come back to circuits with current sources, we'll have to modify this a little bit. So maybe step 0, we'll say identify all meshes label the mesh currents, including their directions. Okay, so I've chosen a direction. Step 0. Now, if you follow nodal analysis, you'll see that there's something similar here. We're going to use apply, we'll say, KVL around each mesh. Write the voltage drops in terms of the unknown mesh currents. Okay, and I urge you to maybe pause this video and go back and look at what we did. Look at the steps for nodal analysis. You'll see something very similar here. All right, and I do want to point out at this point that if there are n meshes, nm meshes, then there are nm unknowns. For example, here we have 2 meshes, right? And so we have 2 unknowns, I1 and I2. Okay, so let's do step 1 here. So we'll do KVL around mesh 1. Alright, so I like to start at the top left and work my way around the mesh. Wherever you start is up to you, it doesn't matter. But stay consistent. So I'll start here, node 2, and I'm going to go in the direction now, this is important, go in the direction that you've chosen for your mesh current. So I've chosen clockwise, so I'm going to start at the top left, and I'm going to go clockwise around mesh 1, in the direction of I1. So the first thing I get is, I get to this 5 ohm resistor, and I want to write the voltage drop across it, okay, in terms of the mesh current. So if I1 is going through it, the voltage drop from node 2 to node 3 from Ohm's law is 5 ohms times I1. That's the voltage like this. Now I'm going to go this way. I'm going to go around the mesh. So now I'm coming down the shared branch, and I want to know what this voltage drop is across the 10 ohm resistor. And I'm going in the direction of I1, so I'm going from node 3 to node 4. Okay, well, I1 is with me here. Actually, so let me back up. So I'm going to add, because KVL is add the voltage drops. So I have this voltage drop, and I'm going to add the voltage drop. So Ohm's law says that that's going to be the resistance times the current. So 10 ohms times. Now, I'm going with I1, right? Imagine I1 is just circling around this mesh. I'm going clockwise with I1. So I1 is with me. It's in the direction that I'm going. Right? In the direction from positive to negative. But I2 is circling clockwise as well, and in this shared branch, I2 is going up against me. So I'm going to write the current in this 10 ohm resistor as I1 minus I2. Like that. And I'm going to move on now, but make sure you're pausing the video if need be. So now I'm at node 4. And the next component I see is this 10 volt source. Okay, well remember I'm adding the voltage drops. So now I want to know how much does this drop by? Well, by definition of a voltage source, that drops by 10 volts. So plus 10 volts. Right, it drops by 10. Notice the polarity of the battery. It drops by 10. So now I'm here at node 1, down here. And remember, I'm going around mesh 1. So I need to get back to where I started. So I'm here. and I need to come back up here. Well, look at the polarity of this source. Okay, that's an increase of 15 volts, and I'm adding all of the drops. Okay, so because that's an increase, I need to subtract. In other words, it's a drop of minus 15 volts. And I'm back to where I started. So all of this equals 0. Alright, we can combine like terms. I have a 5 ohm times I1 and a 10 ohm times I1, so that's 15 ohms times I1. And I have a minus 10 ohms times I2. Okay, and the constant term here, 10 volts minus 15 volts, that's minus 5 volts, but when I add it to the other side, I get plus 5 volts. And we'll leave it for now. I'll put some stars there. We'll come back to that guy. Alright, now let's do a KVL around mesh 2. Okay, and I'll start at the top left of the mesh, which is node 3. And I'm going to go in the direction that I've chosen for I2, which is clockwise. So the first thing I get to is this 6 ohm resistor. The voltage drop across it is, according to Ohm's law, 6 ohms times I2. Then that puts me at node 5, and I need to drop across the 4 ohm resistor. Right? So according to Ohm's law, that drop is 4 ohms times I2. That puts me at node 1, and I'm going to come back up through the shared branch in the middle. So notice the polarity of the battery. This is now an increase because I'm going up that shared branch. An increase of 10 volts, so I need a minus 10 volts there. That puts me at node 4. And I'm going in the direction now of I2, so I want the drop in this, measured in this polarity. So that's going to be, according to Ohm's law, 10 ohms times, I'm going with I2 now because I'm going up, and I1 opposes me because I1 is swirling around in this way. And that puts me back to where I started. So that all equals 0. Alright, so I've got some like terms here to combine. I've got just the 10 ohms times I1. So that's minus 10 ohms I1. And then I have a 6, a 4, and a 10. So that's 20 ohms I2. And I've got a minus 10 volts, so when I add it to the other side, that becomes positive 10 volts. And I've got it in the same form now as my first equation. Okay, so now I need to solve this system of equations. Now these are only 2 equations with 2 unknowns, so you could probably do this with substitution or elimination fairly quickly. Notice here there's a minus 10 I2 and a positive 20 I2. So if I multiplied this equation, the first one, by 2, and I added it to this equation, then the I2s would drop out. So let me do that. So we'll call this equation 1, call this equation 2. So again, if I'm doing twice, right here, twice equation 1 plus equation 2. Okay, that gives me, so I'll have 30 I1 and a minus 10, so that's 20 ohms times I1. And the reason I'm doing this is because the I2s drop out, and then over here I've got 10 plus 10, so this is 20 volts, and I1 then is 1 amp. So that's our solution so far, part of our solution anyway. 1 amp. So there's this hypothetical current, and we'll address that in a second. But that hypothetical current that's swirling around there, that's 1 amp. So what does that make this hypothetical current? Well, I can choose either equation 1 or equation 2 now that I know that I1 is 1 amp and find what I2 is. So I'll just plug 1 amp in for equation 1. So I've got 15 ohms times 1 amp minus 10 ohms times I2 equals 5 volts. So this is 15 here. So when I subtract that, I get 10 ohms, I2, 15 minus the 5 gives me 10 volts. So that implies I2 is also 1 amp. Okay, they're both 1 amp. So I'm going to write our results. 15. Yes, I'm going to write our results right here because I'm going to erase this work. So I1 is 1 amp, I2 is 1 amp. Again, feel free to pause the video if need be, but I'm going to erase this now. And we'll say step 3 then, or excuse me, the third step is solve your NM equations for the NM unknowns. Right? We had 2 equations and 2 unknowns, so we solve those guys. So let me delete this here. Now, in this problem, we got that the 2 mesh currents, the hypothetical mesh currents, happen to be equal. That is just a coincidence. That won't always be true. In general, it's not true. But now let's remove ourselves from this hypothetical nature and talk about actual currents. So we might want to know, what is this branch current that I'm writing in lavender? Call that I1. That's the power supply, the 15-volt supply current. How much current is that thing supplying? Okay, we might want to know that. We might want to know how much current, again in lavender, is going through this 4 ohm resistor. Let's call that lowercase I2. Okay, and we might want to know how much current is traveling down through that shared branch. Call that I3. Okay, these are real currents now. They're not hypothetical anymore. Well, to answer this, first notice that I1, the mesh current, I1, capital I1, is the only mesh current of the 2 that's contributing to this branch. Okay, that must mean then that branch current I1 is equal to I1, mesh current I1, 1 amp. There has to be 1 amp going up, because that's what capital I1 was, and capital I1 is the only thing contributing to this branch. Similarly, over here at the rightmost branch, lowercase I2, branch current I2, is equal to capital I2, because mesh current I2 is the only mesh current contributing to I2, branch current I2. and they're in the same direction, so they're equal. So there's 1 amp there, going through this 4 ohm resistor, going through this 6 ohm resistor. Now we might ask, what about I3? How much current is traveling through I3? Well, for this, we said that that branch current was, and notice I've drawn the arrow down, so that's in the direction of I1, capital, and it's opposing I2. So I3 here, lowercase I3, in this case is 0. Okay, again, that's not always true in general, just for this specific problem. Also, if you didn't follow that, we could equivalently have done KCL here at this node, and we have I1, 1 amp entering, and we have I2 leaving 1 amp, so that leaves 0 amps to go through this way. Okay, so this took, just to summarize, this took 2 equations. The number of equations was equal to the number of meshes. Right? 2 equations in this case. And remember, we said nodal analysis in this problem would have also taken 2 equations. So they're about equal in this particular example. Let's look at another example. So I'm going to delete all of this here. Okay. Two voltage sources, 30 volts, 45 volts, 2 ohms, 9 ohms, 12 ohms, 4 ohms, 3 ohms. Right, and we want to find, well, we want to solve the circuit, meaning we want to find, how about everything in this circuit. So we want to find all of the branch currents, and we want to find all of the node voltages. Call this node 0, 1, 2, 3, 4, 5. Okay, so if you were to use nodal analysis, okay, we have the 6 nodes, excuse me. 6 nodes minus 1 for ground, minus 2 voltage sources. So that would be 3 equations we would need. Yikes. Alright, well, how many meshes do we have here? Well, we've got this mesh, and we've got this mesh. So we've got 2 mesh analysis. We have 2 equations. Hooray! Right, that 2 is less than 3, so the analysis is less complicated, less complex if we use mesh analysis. Also note that Ohm's law does not immediately apply here because we don't know the voltage across any resistors. And there are no parallel resistors, there are no series resistors. Okay, so we have to use nodal analysis or mesh analysis. Alright, so we'll apply those steps from the previous slide. So I've already indicated a direction for each mesh, and I will label these capital I1, capital I2. So let's do KVL around mesh 1. Alright, so I'll start at the top left, which is node 2 in this case. And I'm going to go in the direction of I1, so that's clockwise. So the first thing I hit is this 2 ohm resistor. So the voltage drop, okay, from here I'm going in the direction of I1. So the voltage drop from here to here, Ohm's law tells me that that's the current from here to here, which is I1 times the resistance. So it's 2 ohms times I1. Now that puts me at node 3. I'm going to go around mesh 1. So now I've got the 12 ohm resistor. So the voltage drop using Ohm's law is 12 ohms times the current in that resistor. I1 is going with me, and I2 is opposing me. So the current then is I1 minus I2. That puts me at node 0, and I'm going to go this way, around mesh 1. So I'm going across the 4 ohm resistor. So the voltage drop there is 4 ohms times I1. That puts me at node 1, and I'm going to go up by 45 volts, so that's an increase. Notice the polarity of the voltage source. So I'm going to increase by 45 volts, so that's a minus 45 volts. And I'm back to where I started, so that is 0. So let me combine some like terms. I've got 2I1 and 12I1 and 4I1. So 16, 17, 18 ohms times I1. Is that right? 12, 16, 17, yeah. Alright, and then I have a minus 12 I2. And then when I get the 45 over to the right, I've got 45 volts there. And I will star that so it pops more, so I can come back to it. Alright, let's do KVL around mesh 2. Alright, so I'll start at the top left of mesh 2, and that happens to be node 3. I'll go in the direction of my chosen mesh current direction. So that's 9 ohms is the first thing I get to. And the voltage drop from here to here, node 3 to 4, is 9 ohms times I2. That puts me at node 4. The voltage drop across this component, well, that's 30 volts. So I will add 30 volts to that. That puts me at node 5, and the drop from here to here. Okay, I2 goes with the drop, so that's 3 ohms times I2. Now I'm going to come up the shared branch, going up back to node 3. So this is 12 ohms times I2 is going with me now, right? Because I'm looking at the drop this way, that polarity. So I2 goes with that drop. I1 opposes that drop. So I've got I2 minus I1, and I'm back to where I started, node 3, so that's 0. Alright, so I'll combine some like terms. This is minus 12 ohms times I1. And I've got 12, 3, that's 15, and 9, so that's 24 ohms times I2. And I can subtract the 30 volts to the right, and that gives me an equation that is in exactly the same form as equation 1 up there. I'll call this equation 2. So again, I need to solve that system of equations. Only two equations, right? That's why, in part, why we're doing mesh analysis here, because that's less than nodal analysis. So again, notice it works out this time, just like it did last time, that if I do twice, it won't always be this case, twice equation 1 plus equation 2, if I do that, then the I2's drop out and I can solve for I1. So let's do that. So this would be 36 minus 12, which is 24 ohms. I1. Again, that's twice, so that's 36 minus 12 is 24. The I2's cancel, and then when I do twice this, I get 90 minus 30, so that gives me 60 volts. And so this immediately implies then that I1 is 60 over 24 volts, and there is a 12 there, so that's 5 over 2, 2.5 volts. Excuse me, amps, because I have volts divided by ohms. Amps. Equals I1. So that's part of our solution. Okay, so let's find what I2 is. So I can take this result and plug it into either equation 1 or equation 2. Let's just do equation 1. So this gives me 18 ohms times, we'll keep it as 5 halves. 5 halves amps minus 12 ohms times I2 equals 45 volts. Okay, so 18 times 5 halves, that is 9 times 5, that's 45 volts, minus 12 ohms, I2 equals 45. Alright, so again, and unfortunately we're going to get a branch current here, that's I2, we're going to get a mesh current that is equal to 0. So that's our other solution. I2 is equal to 0. Alright, remember these are the hypothetical currents. So now let's talk about the real currents, the branch currents, i.e. how much current is this thing supplying? Call it I1. How much current is this thing supplying or absorbing? Call that I2. And what is this shared branch current there? Call that I3. Alright? So we want to find those real physical branch currents. So I1, branch current I1, well, only mesh current I1, capital, is contributing to branch current I1. So, and they're in the same direction. So capital I1 is equal to lowercase I1, which is 2.5 amps. So as a side note, that power supply there, the 45 volts, is supplying 45 volts times 5 halves amps. Watts of power, right? Okay, so what about I2, branch current I2? Well, similarly, only mesh current I2 is contributing to branch current I2, and they're in the same direction. So I2 is equal to capital I2, which is 0. So a side note here would be that the power in the 30 volt is 0. It's not supplying or absorbing power because there's no supply current there. So what does that make branch current I3? Well, the direction that I've chosen is down, so that's going with mesh current I1, and I2 is opposing it, so that's I1 minus I2, which is 2.5 amps. It has to be, because if you look at KCL at node 3, you've got 2.5 amps coming in, 0 amps leaving this way, so all 2.5 amps must be going down. Okay, so there are our branch currents. So we've got 2.5 amps out this outer mesh. Or no, excuse me, the left mesh here. The left mesh, there's 2.5 amps just going around like this. So the 2.5 amps goes through the 45 volt source, through the 2 ohms, through the 12 ohms, through the 4 ohms, and back like this. And there's no current going this way, through the 3 ohms, through the 9 ohms, through the 30 volts. Okay, maybe you're interested in voltages now. So I'm going to clean up the picture a little bit. Let's clean up the picture. Remember, kind of to solve a circuit, we'd like to know the voltage everywhere and the power, the voltage everywhere and the currents everywhere. And once we have all that, we can get the power in each component, and then you pretty much have everything you need. So we're calling this node 0 down here. So let's call this ground. Oop. Here's ground. Okay, so that's our reference. So this node down here, okay, we're calling that 0 volts, our reference. So how much voltage is here then? Okay, call that V1. Well, V1, I'll do this in blue. Notice, again, that branch current I1 is 2.5 amps. So that 2.5 amps is coming this way, from the reference node to V1, 2.5 amps, and then up, 2.5 amps. So the voltage across the 4 ohm resistor, from right to left, in the direction of I1, is 0 minus V1, okay? In other words, from Ohm's law, that is I1 times 4 ohms. But I1 is 2.5 amps, so this is 10 volts. So, V1 is negative 10 volts. You see, the drop, the current in a resistor always goes from high potential to low potential. The very first video, the marble rolls down the ramp. So I1 is going this way from right to left. So this is the higher potential. We're calling that 0. And what's the drop? Well, from Ohm's law, the drop is 10 volts. So if this is what we're calling 0 to be, then this must be minus 10. Okay. Now, what about node voltage V2 up here? Well, if this is minus 10 and we increase by 45, then this must be 35 volts. Alright, what about voltage V3? Well, again, we can use Ohm's law. We see that the voltage across the 2 ohm resistor must be the voltage from, in the direction of the current is the voltage at the left minus the voltage at the right. So this is 35 volts minus V3, okay, which is 35 volts And then from Ohm's law, the drop is I1 times 2 ohms. Okay, so the drop is 5 volts. So that means that V3 is 30 volts, because the drop must be 5. If the drop is 5 in the direction from left to right, then from Ohm's law, 5 divided by 2 is 2.5 amps from left to right. And that's exactly how much current we have going through that 2 ohm. Right, so if this is 30 volts, so we've got this node voltage, this node voltage, this node voltage, this node voltage. What's the node voltage at 4? Right here. V4 equals how much? Well, I2 we found to be 0. So 0 current through a resistor means 0 voltage drop across the resistor. That is, the marble is not moving, so the two ends must be at the same height. So if the two ends of the ramp are at the same height, and one end is at 30 volts, that means the other end must also be at 30 volts. And notice KVL is satisfied if we're at 30 volts here. Now we drop by 30 volts, and that puts us down here, right? So V5 is at 0 volts, and it has to be, because there can't be a difference in voltage here because there's no current through the 3 ohm. So this is 0 over here, and this is 0. So everything is consistent. All right, let's do another example, slightly more complex, with a dependent source. All right, so we will start with a voltage source independent of 24 volts. 10 ohms, 12 ohms, 4 ohms. And then we'll say, here's our dependent voltage source, and it's 4I0, and we'll call I0 to be this current here. $24 ohms. Okay, so the voltage drop from here, this is a current-controlled voltage source. The voltage drop from here to here is 4 times whatever this current is. That's tricky. All right, could we use nodal analysis for this? And yes, you can use nodal analysis for any circuit that you see in this course. And that would require this. We could set this to be ground. That would require actually just one equation right here. So nodal analysis would be a good choice for this circuit, but as we're learning mesh analysis, we're going to stick with mesh analysis. So I'm going to identify the 3 meshes here. There they are. Call this I1, I2, and I3. Notice how I stay consistent in the directions that I pick. Unless I'm told otherwise, I'll go clockwise. All right, and as a side note, that something we're going to need here is that side note. I0, we don't want to use that as an unknown. because we are only going to have 3 loop equations, so we're only going to have 3 unknowns, I1, I2, I3. We do not want to use I0. But we can relate I0 to our unknowns. I0 is in the direction of I1, and I2 opposes it. So our side note is that I0 is I1 minus I2. And whenever I write an equation that I want to use I0, instead I'm going to use I1 minus I2. That way my equations are kept in terms of these 3 unknowns in red. Okay, so I'll just label the nodes so I can reference them. There we go. All right, let's do KVL around mesh 1. So I'll start at the top left and come this way. So I've got a drop of 10 ohms times I0. And I0 is I1 minus I2. That puts me at node 2. And my drop here across the 12 ohm resistor is 12 ohms times, okay, I1 is going with me, I3 is opposing me. So I1 minus I3. That puts me at node 0. I got to get back to node 1 where I started. So I need to increase by 24 volts. So that's a minus 24 volts equals 0. So let me combine some like terms. I've got a 10 and a 12. That's 22 ohms times I1. And I2, I've got a minus 10. And I3, I have a minus 12 ohms. I3, and I'll add the 24 volts to the other side. And we will come back to this. Call that equation 1. Alright, let's do KVL around mesh 2. Alright, so I'm going to start at the top left of mesh 2 and work my way in the direction of I2. So this would be 24 ohms times I2. That puts me at node 3. I'm going to go this way, plus 4 ohms times, I'm with I2, and I3 is opposing me. Now I'm here at node 2, and I want to get back to where I started, so I need the drop across that 10 ohm, so that's plus 10 ohms times I2 is with me, I1 opposes me. In other words, I'm going this way, so it's the opposite of I0, I2 minus I1. Back to where I started, so all of this equals 0. So let me combine some like terms. I've got minus 10 ohms I1. I've got a 24 and a 4 and a 10, so that makes 38. 38 I2. And I have a minus 4 ohms I3 equals 0. Okay, and so that's in the same form as equation 1. So we'll put some stars there, and we'll label that equation 2, and we'll come back to it. Alright, now equation 3, so that's KVL around mesh 3. So this time we have the voltage, the dependent source to deal with here. So we'll start at the top left, we'll work our way around. So the first thing I get to is the 4 ohm resistor. The voltage drop across that 4 ohm resistor is 4 ohms times, I'm going in the direction of I3, and I2 opposes me, So I3 minus I2. That puts me at node 3, and I've got to traverse this dependent source now. So the drop is 4, notice the polarity, so that's a drop. That's what I want, that's positive. 4I0. Okay, I0 is I1 minus I2. Okay, that was our side node. Whenever I want to write I0, instead I'm going to write I1 minus I2. That keeps everything in terms of those 3 unknowns. Okay? Can't have 4. So if you have 4, you won't be able to solve your system of equations. So that puts me at node 0, and now I need to traverse this 12 ohm resistor. Its drop is 12 ohms times I3 is with me. Hopefully you're with me. I1 is opposing me. And that puts me back to node 2, where I started. So that's equal to 0. Combining like terms, I have 4I1 and a minus 12I1, so that makes minus 8 ohms I1. For I2, I've got a minus 4 and a minus 4. That makes a minus 8 I2. Okay, for I3, I've got a 4I3 and a 12I3, so that makes 16 ohms times I3. All right, and there's no constant terms there, so that equals 0. And so this is equation 3. Now, if you like, you can simplify your equations a little bit more. In this one, in equation 3, we can divide by 8. Okay, in equation 2, we can divide by 2. Equation 1, we can divide by 2 as well. Okay. But we have 3 equations here, and so you can try to solve this with your eliminations method. But we're going to put this in a matrix, and we're going to use reduced row echelon form, similar to what we did with nodal analysis. So just going to put a matrix here, and our first equation is, well, 22 is multiplying the I1, so I'm going to put 22 there, and negative 10 is multiplying the I2. And negative 12 is multiplying the I3, and the constant term is 24. Okay, so this column is the I1 column, this column is the I2 column, this column is the I3 column, and this column is the constant. So the next equation is negative 10, 38, negative 4, 0. And the third equation is minus 8, 16, 0. And I'm going to put that in reduced row echelon form. So let's do that. Again, your calculator, or MATLAB, or applications online you can use. So this is going to be a 3x4 matrix. 3 rows by 4 columns. Set matrix. So the first is 22. 22. And negative 10. Negative 12. 24. Negative 10. 38. Negative 4, 0, negative 8, negative 8, 16, 0. Alright, so we'll click solve, and there we go. So it gives us our solution set. And again, this one in particular is not extremely helpful because it does not really show the result of the matrix. If you plug this in your calculator or MATLAB, what you'll see is the following: 1/0/9/4, or in fractional form, 0/1/0/3/4, 0/0/1/3/2. Okay, that's what you would get. That's when you put this matrix in reduced row echelon form. So now this first equation says that 1I1 plus 0I2 plus 0I3 equals 9/4. In other words, I1 is equal to 9/4 amps. See, so you can read the solution right off of it. This is I2 is 3/4. And I3 is 3/2 amps. Alright, so now those are the hypothetical currents that are swirling around. So let's look at our branch currents now. Call this I1. How about this guy, I2? And this guy's I3. And this guy, I4. Lots of branch currents. I5. Okay, let's find all of those currents. So, first of all, I1, only mesh current I1 is contributing to the branch current I1. So, and they're in the same direction, so they're equal. So branch current I1 is 9/4 amps. So, this 24 volt source is producing 9/4 amps. Now how does that 9/4 amps split? Okay, well it splits into I0, which we already said is I1 minus I2. So that's 9/4 amps minus 3/4 amps, 6/4, 3/2 amps. Okay. So this 9/4 amps comes in, 3/2 goes down through the 10 ohm resistor. How much goes this way? Well, I4, we could use KCL, but notice that I2 is the only thing contributing to branch current I4. So, and they're in the same direction. So I4, branch current, is equal to mesh current I2, which is 3/4 amps. Okay, what about I3? Branch current I3. Well, notice that capital I3, mesh current I3, is in the direction of branch current I3. So this is capital I3, and mesh current I2 opposes me. So this would be 3/2 amps minus 3/4 amps. Okay, this is 6/4 minus 3/4, so that's 3/4 amps. 3/4 amps going this way. Okay, that leaves, I guess we have I2 and I5. I2, branch current I2. Well, capital I1, mesh current I1, is going with it, and capital I3, mesh current I3, is opposing. So we have I1 minus I3, so that's 9/4 amps minus 3/2 amps. So 3/2 is 6/4, so this is 3/4 amps. 3/4 amps coming down. Finally, I5. So only mesh current I3 contributes to I5. So that must mean that's true, and that branch current I5 is 3/2 amps. So there are the currents everywhere in that circuit. If we wanted the voltages somewhere everywhere in the circuit. Okay, we've already called this node down here to be node 0, so we'll call this ground. So this node 0 is 0 volts. So what's the voltage here at node 1? Well, it's 24 volts higher than node 0. And node 0 is at 0, so this voltage is at 24 volts. Okay. What's the voltage at node 3? Call that V3. Well, we can use Ohm's law. We know the drop across the 24 ohm. The drop is I4 times 24 ohms. Okay, and I4 was 3/4 amps. So that makes 18 volt drop. So there's an 18 volt drop across the 24 ohm resistor, and the top of that resistor is at 24 volts. So if it drops by 18, that means V3 is 6 volts. 6 volts right here. Okay, what about node 2? What is its voltage? Alright, well, we could get this in a couple ways. Notice that I'll just choose to find the drop across the 12 ohm resistor. So the 12 ohm the drop across the 12 ohm resistor is I2 from Ohm's law times 12 ohms. Well, I2 was 3/4 amps. So 3/4 amps times 12 ohms, that's 9 volts. So there's a 9 volt drop in the direction of I2, in this direction. So if this is 0, at the bottom of the hill, or the bottom of the ramp is 0, then what must have been the top? 9 volts. Therefore, V2 is 9 volts. 9 volts. So we have the voltages everywhere. We have the currents everywhere. And we could get the powers if we like. Okay, so go ahead and practice that with the homework, and in the next video we'll introduce current sources to our mesh analysis.